Hi, I'm Bob. Let's do the computer exercises at the end of Chapter 3, the multiple regression analysis, together. I used Stata to find the detailed solutions to the exercises. You can download all the datasets from the link below. I will also attach the do file. Here's the computer exercise number 1. For the first question, beta 2 is most likely to be positive. Higher income generally leads to access to better prenatal care and nutrition for the mother. Their children are more likely to be heavier as a result. For the second question, the cigarettes smoked per day during pregnancy could be positively correlated with family income because a wealthy woman could afford the money to smoke. But the correlation between them could also be negative because higher income families care more about health and the mothers are less likely to smoke during pregnancy. For the third question, the estimated equations with and without family income are as follows. With family income in the model, one more cigarette reduces infant birth weight by 0.46 ounces. Without accounting for family income, one more cigarette reduces a newborn baby's weight by 0.51 ounces. The omitted variable bias is negative. The reason is that family income positively affects infant birth weight and negatively correlates with smoking during pregnancy. The difference in the estimated effect of smoking on birth weight is around 0.05 ounces per cigarette. It is not substantial because family income has a small effect on birth weight, and the correlation between family income and smoking is also small. Actually, we can go further to verify this relationship. The omitted variable bias is beta 2 times the slope estimate from the regression family income on cigarettes. The estimate is minus 0.543, a negative relationship between income and smoking. Suppose the multiple regression represents the population model. We can verify the omitted variable bias formula. Let's go to computer exercise number 2. We use the command describe to find the information on the variables in the dataset. House price is measured in thousands of dollars. We regress price on square feet and number of bedrooms. The equation form of the result is as follows. Holding square footage constant, an additional bedroom increases the house price by $15,198 on average. Adding a bedroom that is 140 square feet, the size of the house increases by 140 square feet, and the number of bedrooms increases by 1. As a result, the house price is estimated to increase by $33,179. In Part 2, the house's total size is fixed, so adding one more bedroom leads to a decrease in the other room size. In this part, we allow both explanatory variables to change. The R-squared is 0.6319. 63% of the variation in price is explained by square footage and the number of bedrooms. For the fifth question, we plug the size of the house and the number of bedrooms in the OLS regression line. The predicted selling price is $354,605. The actual selling price is $300,000. The residual mu hat equals the actual price minus the predicted price, that is, minus $54,605. It suggests that the buyer underpaid for the house. However, we should keep in mind that there could be omitted variables in the model. Without accounting for those relevant factors, we could not conclude whether the house is overpaid or underpaid. Let's solve computer exercise number 3. We use the dataset and describe it and find 177 chief executive officers and their salaries. We also find the firm sales and market value. For the first question, we regress log salary on log sales and log market value. The coefficients on the explanatory variables are the elasticities. The OLS regression line is as follows. For the second question, we add profit to the model. 9 firms have negative profits. We cannot use the log term of profits if we want to have the same sample size. The estimated equation is as follows. The profit effect on salary is tiny. The 3 firms' performance variables can explain 30% of the variation in CEO salaries. For the third question, we add the variable CEO tenure to the model. The CEO salary increases by 1.17% for one more year of tenure, holding other factors fixed. For the fourth question, we type correlate log market value profits. The correlation coefficient is 0.7769. The log of the firm's market value is highly correlated with the firm's profits. First, the correlation between the two explanatory variables will not cause the OLS estimates to be biased. Second, the standard error for the log market value increases when profit is added. The reason is that the R-squared from the regression profit on market value is large because they are highly correlated, so the variance inflation factor is large. The standard errors of the error term sigma hat and sigma tilde are similar, so the standard error for market value becomes larger when profit is added. It is 0.064 versus 0.050. Let's do the fourth computer exercise. We load the dataset and use the command summarize to obtain the minimum, the maximum, and the sample mean values for the three variables. We regress the model. The estimated equation is as follows. The intercept coefficient has no useful meaning because it is the predicted attendance rate if the ACT score and the cumulative GPA are both 0. It is beyond the range of the variables. For the third question, the estimated slope coefficient on cumulative GPA is positive, 17.26. It suggests that one more point in GPA increases the attendance rate by 17.26 percentage points, holding ACT scores fixed. It makes sense that the students with better academic performance tend to attend classes more frequently. The estimate on the ACT score is minus 1.72. It means that one more point in the ACT score reduces the attendance rate by 1.72 percentage points, holding GPA constant. It implies that students with higher ability, measured by ACT before going to college, are more confident than other students that they can pass the college course without attending the class. For question number 4, we plug the values in the OLS estimation equation. The predicted attendance rate is 104. It is impossible since the maximum attendance rate is 100. It is due to two reasons. First, the linear regression cannot fit the data very well if the true relationship is nonlinear, especially for extreme values. Second, there were omitted variables in the model. The OLS estimates are biased and cannot predict accurately. There's one student with these values of the explanatory variables. The actual attendance rate is 87.5 percentage points. For the fifth question, we plug in the values and find that student A's predicted attendance rate is 25.84 percentage points higher than student B's. Let's go to computer exercise number 5. It is about the parceling out interpretation of multiple regression. In example 3.2, we regress the log hourly wage on education, experience, and tenure. We can obtain the estimate for the coefficient on education in 2 steps. In the first step, we regress education on experience and tenure and save the residuals. The residuals are the part of education that is uncorrelated with experience and tenure. In other words, the residuals are the part of education after the effects of experience and tenure have been parceled out or netted out. In the second step, we regress the log wage on the residuals. The estimated coefficient on the residuals is identical to the estimated coefficient on education from the original multiple regression. In both models, the coefficients are the education effect on log hourly wage after the other variables' effects have been parceled out. Let's solve computer exercise number 6. It's about the omitted variable bias when we exclude a relevant variable from the model. We need to verify the relationship between the coefficient from simple regression and the coefficient from multiple regression. Beta 1 tilde equals beta 1 hat plus beta 2 hat times delta 1 tilde. Delta 1 tilde is the slope estimator from the simple regression of IQ on education. It is 3.534. Beta 1 tilde is the slope estimator from the simple regression of log wage on education when IQ is excluded. It is 0.0598. Beta 1 hat and beta 2 hat are the slope estimators from the multiple regression log wage on education and IQ. Finally, we can verify the equation. The equation indicates that the slope coefficient on education is different between simple regression and multiple regression. The difference is the omitted variable bias.